So this is going to be the fourth section of the third chapter stats. Sorry, getting my stuff confused here. About setting standardized scores or z-scores. So z-scores is a very key concept in stats. So this is going to be kind of a core thing going forward. So again, if you need to rewatch this or something, maybe bookmark this in case you forget. That would not be a bad idea. Let me just do a mic check here. Okay, it's still going. All right. So what is a standardized score? So a standardized score is basically allowing us to compare two items that have different units of measurement. So it's kind of like that coefficient of variation we talked about in the last video, where if I want to compare how heights change compared to how weights change, well, the problem is I measure them using two different scales, one for pounds, one for inches or feet, and therefore they're kind of hard to analyze together, so you have to set them in some sort of standardized way. And standardized just means that you set them so that they're on the same type of measurement scale, and you can kind of compare them more validly, if that's a word. So coefficient of variation is a type of standardized score that we did last time. We set it to a coefficient of variation, which was a percentage value. Once we had them into both a percentage type value, then we could compare them about what's more, what's less, and again, any other number of things there. Now, standard deviation is going to be kind of our go-to here. So standard deviation is going to be kind of the core of how we set up these next standardized scores rather than the coefficient of variation. So this is going to be a type of score we call a z-score. So a z-score, again, I remember it from way back when, but I forget about it now. I'm not sure why it's called the z-score rather than an s-score for standardized, but it's just called the z-score. We'll go with that now. I'm sure there's a reason for it. If you want to look it up, be my guest, but I forget it right now, and I don't really feel like looking it up right now. So a z-score is basically a measure of how many how many standard deviations something is away from the mean. So a z-score is not, if you say something has a z-score of 5, that means it's 5 standard deviations away from the mean. Remember, a standard deviation is that measure of spread we talked about a few videos ago, about how far on average something is from the mean value. So let's say your mean value of some set of data, just picking at random here. Come on. Let's say you have a mean value, which is x bar. Your mean value was 10, and you have a standard deviation of 2. So let's say you're talking about, the age of people in a hospital. So you have a hospital, you say the average age of a person in the hospital is 10. Maybe it's a child care hospital. And you come across somebody who is 14 years old. You come across somebody who's 14 years old. Well, how many deviations away from the average are they? Well, if the standard deviation is 2 and they're 14 years old, that means they're 2 standard deviations away from the mean. Because you jump once, you get to 12. Jump another time, you get to 4 if you're jumping 2 each time. So they're plus 2 standard deviations away from the mean. They're 2 deviations higher from the average. So they would have a z-score of 2. That's all a z-score is how many standard deviation jumps are you from the average value. And as we said before, 2 deviations above and 2 deviations below are the maximum usual and unusual values. So a z-score of 2 or -2 is the maximum z-score you would have to be usual before you start getting to that unusual territory. So let's go over how to get a z-score here. And again, it's fairly simple arithmetic-wise. So all you do is you take the value. So remember, x is the value that you're looking at. So this would be like the 14 in our previous example, minus the average. So remember, x bar is the average, divided by the standard deviation, which is that lowercase s there. For a population, same thing. It's just population average and population deviation. Nothing really new there. But again, for the most part, we're going to be dealing with the sample ones. So again, it's just figure out how far away the value is from the average and then divide it by the standard deviation, because that's all you're doing. Again, I keep repeating this, but that's because it's important to get that in your head, because people think z-scores are some weird, strange calculation. All they are is how many deviation jumps are you from your average. That's it. That's all it is how many deviations jumps are you from your average. Usually you round them to the nearest hundredth unless otherwise specified to. And again, they are a unitless measurement. So it's not like 2 years or 5 years. It's just 2 deviations, 3 deviations, 4 deviations. They don't have a unit associated with them so that we can compare them, because that's the whole point. If we can convert two things into a z-score, we can compare their z-scores even if their original values have different types of units like inches and pounds. So again, let's compare heights here. So not only is this useful for comparing things of different units, but it's also comparing things of different categories. Like if we compare the heights of, say, presidents to the heights of, say, basketball players. So let's say we want to figure out who was taller, Lyndon Johnson or Shaquille O'Neal. Well, Lyndon Johnson wasn't a basketball player, obviously. So let's compare them in terms of their group. So was Lyndon Johnson a taller president than Shaquille O'Neal was a taller basketball player? Because the heights of presidents are going to be a lot different than the heights of basketball players, especially pro basketball players. So it wouldn't be fair just to compare Lyndon Johnson's height to Shaquille O'Neal's height and say, well, Shaquille O'Neal was taller. Well, yeah, that's true. But if we compare Lyndon Johnson to the group of presidents and compare Shaquille O'Neal to the group of basketball players, which one was taller for their group? Was Lyndon Johnson a taller president or was Shaquille O'Neal a taller basketball player? So to do that, we're going to convert them into z-scores. We're going to see how far away they are from the average, and then we can deduce who was actually the taller person among their peers. So let's take Lyndon Johnson's first. Lyndon Johnson was 75 inches high, pretty tall president. The average height for presidents, at least from when this data was taken, was 71.5 inches, and the deviation was 2.1 inches. So to get his z-score, we're going to take his value, 75, minus the average to figure out how far away from the average he is, and then divide it by the deviation to figure out how many deviations he is from that average. So if we do this here in our calculator, we do 75 minus 71.5, and we get 3.5. 3.5 divided by 2.1, and we're going to see how many deviations he is from his average, which is about 1.6 repeating. So if we round to the nearest hundredth, it'd be 1.67. And I'll put SD here for standard deviations. So that is his z-score, a 1.67 z-score. So he's not an unusually tall president. Even though he's kind of a tall guy, he's not an unusually tall person for presidents there, because he's only 1.6 deviations above the average. So let's see if Shaquille O'Neal was a taller basketball player. So Shaquille O'Neal had a height of 85 inches, so we're going to put 85 here, minus what's the average height of a basketball player, at least when this data was taken, was 80. So minus the average of 80 divided by the deviation, which is 3.3. So if you notice here, the first thing you can tell is that basketball players seem to have a higher standard deviation than presidents, which means that presidents were kind of all around the same height, at least more than basketball players were. So this means that basketball players vary from pretty tall to pretty short a lot more than presidents do. Just some tidbit that you can use as a reference there. So that'd be 5 over 3.3. So 5 divided by 3.3, we get 1.52 if we round it off there. So 1.52, not inches, but standard deviations. Okay, so this is not 1.52 inches or 1.67 inches. These are deviations here. So he is only 1.52 deviations above the average basketball player's height. So in this case, it would seem that Lyndon Johnson was a taller president than Shaquille O'Neal was a tall basketball player. So Lyndon Johnson was taller than average for presidents than Shaquille O'Neal was for a basketball player. Now, again, Shaquille O'Neal is still, or I should just say Shaq because it's a lot easier to say, Shaq is still a taller guy in all because, again, 85 is more than 75, obviously. But among their peers, Lyndon Johnson would be considered taller for his group of people, which is the presidents, than Shaq was for his group of people, which is the basketball players. So another way we can say this is Lyndon Johnson was unusually tall for a president more than Shaq was unusually tall for a basketball player. Now, neither of them are technically unusual because remember, unusual means that you're more than 2 above or below, and neither of these are more than 2 above. But if we're talking about compared to each other, Lyndon Johnson was more unusually high for tall for a president than Shaq was unusually high for a basketball player. Because again, you couldn't compare these by themselves because they're from two different groups. One's from a basketball player background, so they're usually taller, and then one's from a president background, which usually doesn't have that much of an influence on height. So we have to kind of do the standardized score here so that we can compare them more accurately. So again, that's it. So Shaq was taller overall, but Lyndon Johnson was taller for his population of presidents. So remember, ordinary values are between 2 and -2 for a z-score, just like you're between 2 and -2 deviations above or below the mean. So remember, negative z-score means you're lower than average, positive z-score means you're higher than average, and a z-score of 0 means you're exactly on the average, essentially. But if you're outside the bounds of 2 or -2, that means you're unusual. Again, that could be a good or bad thing depending on what you're tracking. So Human body has an average temperature of 98.6 degrees with a standard deviation of 0.62. Let's see if we can convert a temperature of 96.8 into a z-score and see if that's unusually high or low. So let's say you go to the hospital, they take your temperature, the temperature is 96.8, and the doctor needs to find out, okay, do you have an unusually high or low temperature compared to this average body temp or not? Should we be worried or not? So let's figure it out here. So remember, the z-score is the value minus the average divided by the standard deviation. So the value that we're tracking is 96.8 minus the average that we have, which is 98.6, divided by the deviation we're given, which is 0.62, right here, 0.62. So we do some math here in your calculator if you want. So 98.6 minus, oh sorry, not 98.6, 96.8, making sure I get the value first, minus 98.6, which is negative 1.8, which is fine. Again, deviations and z-scores can be negative. That's okay. Or I should say z-scores can be negative. Deviations aren't negative, but z-scores can be. Let me erase that line there because it's annoying. There we go. Hopefully that doesn't happen too much here because that gets annoying to erase it every time. And so that divided by 6.2 is negative 0.29 is what I got. Negative 0.29. So that's a pretty close to the average, it looks like. Or at least, oh wait, sorry, I divided that wrong in my calculator. My bad. I thought that should have been higher because 96.8 seems to be pretty low for a body temperature. So I divided it by 6.2 rather than 0.62. So let me try that again. Negative 1.8 divided by 0.62. There we go. That gives us a negative 2.90 essentially, standard deviations. So this guy has or a girl has a body temperature that's negative 2.9, or I should say 0.29 deviations below the average, which is pretty unusual, right? That's borderline 3. So this doctor probably would be in panic mode here saying, okay, they have a pretty low body temperature. We probably need to do something about this because that's an unusually low body temp. Now, if you notice here, this is not that far off numerically from 98.6, right? This is what? Maybe less than 1 point something, or this is like 1.8 degrees below the normal temperature, right? So you might think, well, if you're down 1.8 degrees for your body temperature, that's not that big a deal. It's 1.8 degrees. You can hardly feel that, right? If they said, well, the temperature is going to drop 2 degrees outside, you probably wouldn't notice that. But because the average is, or because the standard deviation is so tight that it has such a low standard deviation, that means a small change actually is a big impact. Because again, this is an unusually low body temperature. This is why, again, another use of standard deviations is to see whether something is actually impactful or not. Because you might think numerically a 2-degree drop isn't that big a deal. But if you look at how tightly the average is contained with the deviation there, how close to the average most body temperatures are, a drop that small is actually quite significant. So even if numerically it might seem like a small change, if your deviation is small or tight like this one is, then that can have a big impact and be quite unusual. Okay? This is probably going to go through the stuff we just did there. Whoops. So this, again, just doing what I did there. I just forgot that these popped up there, so that's my bad. So another thing that we kind of use to help us gauge something is also called quartiles and percentiles. So this is going a little bit away from z-scores right now, but they're similar. So quartiles and percentiles are basically the same thing. Quartiles are a type of percentile. They're just said differently. Quartiles, we'll talk about first, basically quarter your data. They're the 3 values that kind of separate the 25%, the 50%, and the 75% mark. So if this is all your data set here, so if you have a length of data in the numbers here, what the quartiles do is they split it into 4 equal sections. So this is equal to this, is equal to this, is equal to this. So they quarter the data. The first quartile happens at 25%. So 25% of the data is below the first before the first quartile. 50% or half the data is below the second, and 75% or 3/4 of the data is below the third. So if your Q3 is 5, that means 75% of your data is below or at 5. Remember, quartile 2, Q2, is basically the median, because the median is the middle 50% data point there. So if your Q1, let's say you're tracking, again, the ages of people in a hospital, and your Q1 is 3, that means 25% of the people in the hospital are age 3 or less. So Q1 means 25% of your values are at this value or lower. Not more, but lower. And then again, Q2 is 50% or less, and Q3 is 75% or less. So think about quartiles as a this percent or less. Percentiles are simply quartiles that aren't at these marks here. So percentiles like the 23rd percentile, usually called P23, means that this value marks the 23% or less mark. So if your P23 was 2, that means 23% of the people in the hospital are age 2 or less. So percentiles are just the non-quartile sections, but they do the same thing. Quartiles are just these special marks where they separate the data into 4 equal pieces. So the way you find these percentiles or quartiles, again, you can do this for either one. It's just that quartiles, again, they're already known to be 25, 50, and 75. So percentiles are a little bit more general. The way you get your percentile, which we call K here, is you take the number of values less than your desired value, divide it by the total number of numbers you have, kind of like an average almost, and then you times it by 100 to get into a percent form. And you should round your answer to the nearest whole value. So you shouldn't have like the 2.5 percentile. It should just be 3. Okay? And again, you usually write them with a subscript like PK, so it would be the kth percentile. So P15 would be the 15th percentile. P7 would be the 7th percentile. And again, Qs are used for the quartile. So Q1 is the same as P25. So P25 and Q1 mean the same thing. It's just that quartiles have a special notation for them because, again, they quarter the data. They're a little bit special in that case. So let's do an example here. So here's the numbers we have. Again, let's say that these are the, again, I keep running out of things to use, so I usually default to ages because that's the one that's going to make the most sense. Let's say these are the amount of money in people's wallets on a bus, just to give it some context there. So what we would do here is we would take this data set, and we have to put it in order first, which it already is, so that's good for us. We want to figure out the 29th percentile. So again, make sure you put your numbers in order first before you do this. We want the 20, or we want what number, what percentile is the 29? Again, I had to make sure I said this correctly here. What percentile is the 29th mark going to represent there? So what we do is we say, okay, here's 29. How many numbers are less than 29? Now, we're not going to include 29 in that. It's just how many numbers are strictly less than 29. Well, we see here that there are 2 numbers that are less than 29. So we have 2 numbers less than 29. How many numbers do we have total? Well, we have 1, 2, 3, so we do count 29 in this case. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 numbers total. And we're going to times that by 100. So that'd be 0.2 times 100, which would be 20%. So 29 would be the 20th percentile. 20% of my data is 29 or less. That's all it is. So again, number of values that are less than the target number divided by the total number of values you have times 100. And again, this makes sense. If I have 10 numbers and 2 of them are below 29, that means that 20% of my data is less than 29. That's just again, a rule of percentages there. Now, what if we want to work backwards? So this is usually how stuff goes, is you want to say, okay, what value is this certain percentile? So let's say I want to know if given a set of data, what is the 17th percentile? Rather than looking at a number, we're looking at a percentile and getting a value from that. And the way you do that is you basically work backwards using a locator. So a locator would be the position of the number you're looking for. So let me show you kind of how that goes here. So we want to know the kth percentile. Let's say we're asking that. We want to know what the kth percentile is. Well, this is how we normally get the percentile, right? I just swapped out the words we usually use for variables. So these are if you go back to the original equation here, come on. I just swapped out these for variables just to make the writing a little bit easier, okay? So all you do is you basically solve this for L, which again is the number of values less than your target number. So you divide both sides by 100 and then you multiply by n and you get this. So this is basically how you locate the number you want. This is the position, not the number, but the position of the number in your list that you want to find out here. So let's look at these cases. And again, depending on if L is a decimal or not, it switches up a little bit. But let's look at these cases here. Again, you always round up if it's a decimal. So you have a list of numbers here, same list of numbers. You want to know what number is the 70th percentile. Okay, what number is the 70th percentile? So if you look back here, we're going to take 70 divided by 100 and then times by the number of numbers we have. So 70th percentile divided by 100. So basically take your percentile and make it in a decimal, and then times it by the number of numbers we have, which is 10. So we get 0.7 times 10, which is 7. So we're looking not for, 7 is not my answer, but I'm looking for the 7th number. So I'm going to count here. 1, 2, 3, 4, 5, 6, 7. So this is my 7th number. 1, 2, 3, 4, 5, 6, 7. So because this is a whole number, the 70th percentile is a value midway between the 7th and 8th value. So this is the 7th value. This is the 8th value. So I'm going to find the middle of these. So if you don't remember how to do that, you just simply add them together and divide by 4. Or divide by 2. I don't know why I said 4. Divide by 2. And you get 47.5, which is this one right here. So the 70th percentile is 47.5, which is not part of the data, but that's fine. Sometimes your percentile is not actually part of your data set there. And again, the reason we do this here is because think about what the percentile means. Percentile means that 70% of your data is at or below this number. Now, if I just said, well, 41 is my 70th percentile. Well, if that was true, that means 70% of the data is below 41. 1, 2, 3, 4, 5, 6. Well, only 60% of the data is below 41, though. If I say 41 is my marker, only 60% of my data is less than that. So that's why I need to find the midway point here so that I have exactly 70% of the data there. So when I click 41, when I click 47.5, when I mark that down, I know that 70% of the data is strictly less than that. So that's why I can't use 41. That's what we mean by since it's a whole number or since it's like part of the data, I have to go midway towards the next value. So 41, go midway towards the next value up, midway towards 54, and whatever that number is, that's my actual 70th percentile. Because again, I can't say 41 is the 70th percentile because only 60% of the data is below that. So 47.5 would be my 70th percentile. That's why this less than or equal to sometimes gets a little bit weird here. So you can cross out the or equal to part. If that's going to help you avoid using 41 as your actual marker, then cross out the or equal to part and just use 47.5. The or equal to part there really is because sometimes you might have repeated numbers in a value, like you might have 1, 1, 2, 2, 3, 3. And then if this number is your, let's see, 1, 2, 3, 4, 5, 6. So if this number is whatever percentile it is, then this is part of the numbers that are below that value, essentially. So that's why I put the or equal to part in there, just because sometimes it can have repeated values. But if that's going to confuse you, then just say less than. That way you know that when I hit 41, well, there's only 6 numbers less than 41, which is only 60% of my data total. So I need to make sure I go halfway up to the next marker there. So that's why, again, we have that halfway idea there. This is confusing to some people, so again, just make sure you get used to using that item there, and just check at the end. If you got the 70th percentile, make sure that 70% of the data is less than that number, and you're set to go. So this is kind of like a flowchart that sort of summarizes what we did before. So like I said, if you want to find the locator, or you want to find the percentile value, like let's say they give you find the 20th percentile or something like that, you first put the data in order. You then use this formula to get your locator number. So again, this is not your answer. This is simply the position that you're looking for. So this right here gets you the position. Okay. Now, if your locator position is a whole number, like before, like here it was 7. My locator position was 7. Then what you do is you find that 7th mark, and then you go halfway up to the next one. So if your locator number was 8, you would go up to the 8th number, and then go halfway to the next one. If your locator number was 10, you go to the 10th number and go halfway to the next one. Now, if your locator is not a whole number, let's say in the previous example we got 7.5, well, we can't go to the 7.5th number, right? There's no 7.5th number because you can't have a 0.5th position. So in that case, you simply round it up to 8, and then you figure out that number. Now, again, you always round up. So even if you had, like, let's say your locator, your L, was 6.2, you wouldn't go to the 6th number, you go to the 7th number. So you go one number higher. You always round up. So if your locator number is a decimal, it's actually less work for you to do, because all you do is you round the decimal up, find out which number is in that spot, and then you're done. There's no reason you have to go midway or stuff like that. So it's a little bit easier to work with it when L is a decimal rather than a whole number. So I believe, yeah, that ends it here. Come on. Ah, can't get that click right. So that's all for this video. Again, z-scores and percentiles are kind of the key concept here. They both have procedures to get with them. Z-scores hopefully seemed a little bit easier to get than percentiles, which again are a little bit strange at first, but as you practice them, it gets a little bit easier to work with. So again, make sure you look over this a few times if you need to, practice the work. If you have any questions, you can email me, let me know. I'll be happy to answer them. Hopefully this helped you out, and have a good day.